Let us look at complex matrices and conjugate transpose of those matrices. A matrix is called a complex matrix if one or more of its entries is of the form A plus IB, where B is not equal to 0. For example, we have this complex matrix. First row, third element is minus I, and second element in the second row is 11I. So even if one of these elements is of this form where B is not equal to 0, we call it a complex matrix. A complex number Z is equal to A plus IB has a conjugate A minus IB, where the sign of the imaginary part is reversed. And conjugate is represented as Z bar. So if our complex number is Z, then its conjugate is denoted by Z bar. The matrix obtained from A by replacing its elements A sub ij by the corresponding complex conjugate is called conjugate of A. So let's say we have a complex matrix A. Its conjugate would be where we replace all the entries with their conjugates. So we have 1 minus I, we replace it with 1 plus I, which is the conjugate of 1 minus I, minus 2I, plus I, 4 plus I, minus 6I, and 3. Note that A plus IB is a real number when B is equal to 0. So the imaginary part will disappear. So in the above case, 3 can be written as 3 plus I0. Its conjugate is 3 minus I0, which is equal to 3. Hence, conjugating a pure real number does not change it. Now, let us take the transpose of A. Transpose of A would be, here we have columns. Those columns become rows in the transpose. So 1 minus I, 2I minus I is the first column in the transpose. And we have 4 minus I, 6I, 3 as the second column. The conjugate of this transpose is 1 plus I, 4 plus I, minus 2I, minus 6I, plus I, and 3. So this would be the transpose conjugate of A. In short, we can also write it as A star. Conjugation and transpose commute. So either order gives the same result. That means we can call it as transpose conjugate or conjugate transpose, depending on which one is done first. So let's take another example. Let's say A is this matrix where all the elements are complex numbers. Its transpose would be columns becoming rows. 1 plus I, 2 plus I, 3 plus I, 2 plus 2I, 2 plus 3I, 5 plus I, then 3 plus 3I, 4 plus I, 3 plus 2I. And if we take the conjugate of this transpose, we get 1 minus I, 2 minus I, 3 minus I, 2 minus 2I, 2 minus 3I, 5 minus I, 3 minus I, 4 minus I, 3 minus 2I. So pretty straightforward. Now, within this, we have Hermitian matrix. Now, what is that? A square matrix is called a Hermitian if the matrix is equal to its conjugate transpose. So here it is not the case, but if this conjugate transpose is equal to this matrix, then we would call it as Hermitian. Now, A is the matrix containing A sub ij is Hermitian if and only if Aij is equal to the conjugate of Ji bar. for all I comma j. Here, focus on the subscript. Here we have ij, here it is ji. So that is the transpose part of it. And the bar means conjugate. The matrix must be square. Since if A is m by n, then A transpose is n by m. And equality is only possible when m is equal to n. So let's take an example. We have A is equal to 2, 1 plus I, 3 minus I, 1 minus I, 4, and so on. Its transpose would be 2, 1 minus I, 3 plus I, and so on. And its conjugate would be 2, because it's just the real number, 1 plus I, 3 minus I, 1 minus I, 4 minus 2I, 3 plus I, plus 2I, and 5. And here you will notice that the transpose conjugate is equal to the original matrix A. So transpose conjugate of A is equal to A, hence A is a Hermitian matrix. So that was Hermitian matrix. Now let's look at skew Hermitian matrix. Now here, a square matrix is skew Hermitian if transpose conjugate of A is equal to the negative of matrix A. That is, if and only if A sub ij is equal to minus A sub ji conjugate for all ij. So again, let's take an example. We have this matrix A, its transpose is this, and its conjugate, the conjugate of the transpose is this. Factoring out minus 1, we get the negative of A itself. So the transpose conjugate of A is equal to minus A, hence A is a skew Hermitian matrix. So that was complex matrices and conjugate transpose of those matrices. That's it for now. Bye.